Here's a deceptively simple pattern mastery 100 question that's caught many off guard. Same tree. Top companies love it because it reveals your understanding of recursion and attention to structural detail. Over 20% of candidates miss a subtle base case or comparison. Get this right and you'll have recursion fundamentals locked down for your next interview. Let's master same tree using the basic approach, breaking down the problem, analyzing, structuring a solution, and checking all edge cases. Let's break it down. Given the roots of two binary trees, return true if they're structurally identical and all their nodes have the same value. Otherwise, return false. Input: two binary tree root nodes, P and Q. Output: Boolean: true if the trees are the same, false otherwise. Real-world example. Suppose you're building a cloud backup system, and you need to verify if a backup is a true replica of the original tree structure and content. Interviewers might ask, how would you compare two hierarchical document models for structural and content equality? Let's assess. What's tricky? You have to check both the structure and the values at every node. Recursion is the natural fit. You need to handle all the cases where one tree might branch when the other doesn't, or values don't match. Think step by step. If both nodes are null, they're the same at this branch, return true. If only one is null, the trees differ, return false. If both nodes exist, check if their values match. If not, return false. If yes, recursively check their left and right children. The answer is only true if all these checks succeed for every node. Let's add more. Be sure to check both left and right subtrees. Missing one is a classic pitfall. Order of checks matters. Avoid null pointer errors by checking for null before accessing values. Edge cases. Both trees empty should return true. Trees with same shape but different values should return false. Trees with different shapes should return false. Here is the structure. If both P and Q are null, return true. If only one is null, return false. If both exist, compare their values. If not equal, return false. Otherwise, recursively check left and right children. Return true only if both left and right subtrees are also the same. Let's try to implement it using solution 1. Line-by-line narration. Line highlighted, class solution. We begin by defining a class called solution. This is simply where we'll store our function. Pause. Line highlighted, def is same tree self, P, Q. This line defines our function as same tree, which takes two tree nodes, P and Q, and decides whether the two trees are exactly the same in both structure and values. Line highlighted, if P is none and Q is none, here we check the simplest possible case, if both nodes are empty. If both trees hit an empty spot at the same time, that part is considered identical. Pause. Line highlighted, return true. When both nodes are empty, we return true because matching nothing with nothing means the trees still match perfectly. Time complexity note. Base cases are 01. Pause. Line highlighted, if P is none or Q is none, this checks another scenario. What if one node is empty, but the other isn't? That means the trees don't match structurally. Pause. Line highlighted, return false. If exactly one side is missing, we immediately return false. The trees differ. Pause. Line highlighted, return p.val equals q.val, and now we get to the main logic. First, we compare the values stored in the two nodes. If the values differ, the trees are definitely not the same. Pause. Line highlighted, self dot is same tree p.left, q.left, and this line recursively checks whether the left subtrees of both nodes are identical. It dives down the left branches of both trees in parallel. Time complexity. In the worst case, we visit every node on. Pause. Line highlighted, self dot is same tree p.right, q.right, and then we do the same with the right subtrees, comparing them recursively as well. For the entire tree to be the same, all three conditions must be true. Values match, left subtrees match, and right subtrees match. Pause. Final wrap-up. And that's how this algorithm works. It first checks the simple base cases for empty nodes, then recursively compares the values and structure of the left and right subtrees, ensuring every part of both trees matches. Efficient, simple, and elegant. Highlight input box. P equals 1, 2, 3, Q equals 1, 2, 3. Let's test our function with these two binary trees represented in level order form. P equals 1, 2, 3 and Q equals 1, 2, 3. Both describe the exact same structure. 1 is the root. 2 is the left child. 3 is the right child. Explain the logic briefly. Our algorithm checks if the two trees are identical, meaning same structure and same node values. Since every corresponding node matches perfectly, the trees are indeed identical. Highlight output box, output, true, expected, true, and that's exactly what we get. True, matching the expected value. The test case passes cleanly, so our implementation is correct. The algorithm correctly verifies the structural and value-based equality of both trees. Simple, accurate, and reliable. Now let's try another implement approach using solution 2. Line-by-line narration. You're an engaging, coding narrator guiding beginners through each line. Line highlighted, class solution. We start by defining a class called solution, which simply groups our method together. Pause. Line highlighted, def is same tree self, p, q, this function is same tree. Checks whether two binary trees are exactly identical, same structure, same values, same layout. Pause. Line highlighted, stack equals p, q. Instead of recursion, we use an explicit stack. We begin by pushing a pair, the root of tree p and the root of tree q. We'll compare the two trees node by node using an iterative DFS, depth first search. Space complexity, up to on for storing nodes. Pause. Line highlighted, while stack, this loop runs as long as there are node pairs to compare. Every iteration pops one pair from the stack and checks if they match. Time complexity, each node is pushed and popped once on. Pause. Line highlighted, node 1, node 2 equals stack.pop. We pop the last pair from the stack. This is DFS behavior. Last in, first out. These two nodes are the ones we'll compare next. Pause. Line highlighted, if not node 1 and not node 2. If both nodes are empty, that means both trees reach the end of a branch at the same time. That's perfectly fine. We just continue. Pause. Line highlighted, continue. We skip any further checks for this pair and move on to the next one in the stack. Pause. Line highlighted, if not node 1 or not node 2, this checks for mismatch structure. If one node is empty and the other isn't, the trees differ. Pause. Line highlighted, return false. In that case, we immediately return false because the trees are not the same. Pause. Line highlighted, if node 1.val equals node 2.val. Here we compare the actual values stored in the two nodes. If the values aren't equal, the trees don't match. Pause. Line highlighted, return false. Any mismatch in node values means the trees are not identical, so we return false right away. Pause. Line highlighted, stack.append node 1.left, node 2.left. We push the left children of both nodes onto the stack. These pairs will be compared later. Pause. Line highlighted, stack.append node 1.right, node 2.right, and we push the right children as well. This ensures we compare the entire structure of both trees, branch by branch. Pause. Line highlighted, return true. If we finish the entire loop without finding any mismatches, the trees are identical, so we return true. Pause. Final wrap-up. And that's how this algorithm works. It first initializes a stack with both root nodes, then iteratively compares each pair of nodes while pushing their children for further comparison. Efficient, simple, and elegant. Highlight input box. P equals 1, 2, 3, Q equals 1, 2, 3. Let's test our function with these two binary trees represented in level order form. P equals 1, 2, 3 and Q equals 1, 2, 3. Both describe the exact same structure. 1 is the root. 2 is the left child. 3 is the right child. Explain the logic briefly. Our algorithm checks if the two trees are identical, meaning same structure and same node values. Since every corresponding node matches perfectly, the trees are indeed identical. Highlight output box. Output, true, expected, true, and that's exactly what we get. True, matching the expected value. The test case passes cleanly, so our implementation is correct. The algorithm correctly verifies the structural and value-based equality of both trees. Simple, accurate, and reliable. Quick recap on same tree. It looks simple, but it's a brilliant test of your recursion fundamentals and your eye for structural detail. Exactly why top companies love it. We framed the task as a pure comparison problem. Two roots in, and we return true only if both trees match in structure and in every value. We highlighted why recursion is the natural fit and called out the easy-to-miss cases. Both null is true, one null is false, and any value mismatch fails, plus the reminder to check both left and right subtrees. Our plan was a tight sequence. Handle the null checks first, compare values when both nodes exist, then recursively verify left and right. Both sides must agree for the overall result to be true. We translated that plan directly and ran it on LeetCode, clean execution with no errors. We validated with examples. Identical trees returned true, and differences in shape or values returned false. Test cases passed as expected. The big lesson: recursion succeeds when base cases are exact and comparisons are symmetrical. Nail this pattern, and you're set up for problems like symmetric tree, subtree checks, and beyond.